In this next part, we're going to understand how organic compounds can be classified according to their functional groups. So far, we've seen this in the form of alkenes and alkynes and how they contain specific functional groups. And I'm going to take you through an example in a moment looking at alcohols. This is the science understanding that this video will relate to. So organic molecules have a hydrocarbon skeleton and can contain functional groups. What are functional groups? So essentially, a functional group is a reactive site that can be an atom or group of atoms on an organic compound that can give rise to specific chemical properties. So this can help determine how these particular compounds can react with other substances, and it normally also corresponds to its physical properties as well. What we have here are a range of general skeletal formulae of different organic compounds, and within each of these we can see a specific functional group that makes each of these organic compounds different. We've talked about alkanes, alkenes and alkynes so far. Alkanes don't specifically have a functional group, so they don't have any reactive site that makes them unique and react in a specific way. But when we have a look at the alkenes and the alkynes, it's the presence of that double or triple bond that can often give rise to certain chemical properties. There are more than just what's presented here. There are other varieties of different types of organic compounds, but this just shows you a little snippet of the different types that can exist. Our focus is going to be on these alcohols here. So a bit of background with alcohols. They are unique because they contain what we call a polar hydroxyl functional group. So it's an OH group that is bonded to the carbon chain itself. It's polar because it contains a polar to oxygen to hydrogen bond, and that creates a polar region in the molecule. We know we've got an alcohol if the name ends in ol. So an example would be something like methanol and ethanol. The ol ending indicates that it's an alcohol. Provided that we have one hydroxyl group, alcohols also conform to a general formula. So that would be equal to CnH2n plus 1 OH. And we like to keep the OH together just to indicate that it is an alcohol. We can also classify alcohols as either primary, secondary, or tertiary. To have a look at this, what we have to consider is where this hydroxyl group is bonded to, so what carbon it's bonded to, and then from there work out how many other carbon atoms that is bonded to. So start off with a primary alcohol. What we can see here is that we have this hydroxyl functional group, which is bonded to a carbon, and this carbon itself is bonded to one other carbon atom. This R group here just indicates an alkyl chain, so it's the rest of the molecule that we're not really concerned with, but it should contain some type of hydrocarbon chain. This is different to a secondary alcohol, so we can see in this case the hydroxyl group which is bonded to this carbon is itself bonded to two other carbon atoms or two other hydrocarbon chains. So this is what makes it a secondary alcohol. And finally, with the tertiary, we can see that this hydroxyl group bonded to the carbon is itself bonded to three other carbon atoms. So you just determine how many carbon atoms the carbon bonded to the OH is itself bonded to, and that will determine its classification. Let's have a look at how we can name for a range of alcohols. So keeping in mind that the name ends in ol, and we're going to need to indicate where this hydroxyl group is positioned. So in this molecule here, we can see that the longest carbon chain contains three carbon atoms, and this OH group, we want to position it so it's on the lowest possible carbon number. We know that 3 indicates that its prefix is pro, and we're just going to number 1 to 3 from right to left. And it's going to be a propanol, but we need to indicate where this OH group is positioned, and that's because it can be positioned in many different locations. This hydroxyl group is positioned on carbon 1, so we write this as propan-1-ol or 1-propanol. So I'll write these both underneath. It doesn't matter where you position that number as long as you've indicated it somewhere, whether it's at the start of the name or whether it's in between the propan and the ol. So the propan indicates it's derived from an alkane made up of 3 carbons, and the ol indicates it's an alcohol. So in other words, it contains this OH functional group. Our next example here, so we can see we've got now a different carbon chain. We've got 1, 2, 3, 4, 5, 6 carbon atoms in the longest carbon chain. We have a methyl group on this carbon here and a hydroxyl group on this carbon here. We're going to number it from left to right to give the OH group the lowest possible number. And we know from our previous videos that you would need to name any substituents first. So I'm going to indicate where this methyl group is. And now we need to finish off the name, so indicating that there's 6 carbons in the longest chain, so it's going to be a hexanol, but it's going to be a hexan 3-ol. Alternatively, we could also name this 2-methyl 3-hexanol, and just keeping in mind where those hyphens need to go. Third example, so again, let's determine where our longest carbon chain is, and it's important that it contains the OH group. Now we could have said that it contains 4 in the longest chain, but that's not true because we actually have a long chain of 5 carbon atoms going as such. So this is going to be a pentanol. Let's number the carbons, indicate the methyl groups. We then write the names of where these methyl groups are. So we've got 2 of them, one on carbon 3 and 4. And in this case with 5 carbons, it's going to be a pentan, and we're going to indicate it's on the hydroxyl groups on carbon 2. Next example, in this case we've got 2 OH groups. So like with methyl groups and ethyl groups, to indicate that we're going to put a di prefix, but the difference is that this di needs to go just before the ending of the name, which is ol. We've got here 4 carbon atoms in the longest chain, so it's going to be a butan. And if we number the carbon atoms, we can see that we have these 2 hydroxyl groups, one on carbon 2 and one on carbon 3. To indicate that there's 2, we're going to use the di prefix, so it's going to become a butan 2,3-diol. Alternatively, we can put the numbers in the front, so I'm just going to show you what this looks like. One common mistake that I see is that students put the di in front of everything, so they try to call it a dibutan 2,3-ol or a 2,3-dibutanol, which is not correct. One more example. In this case, again, determine the longest carbon chain, and it needs to contain the OH group. So we've got 1, 2, 3, 4, 5, 6, 7. So it's going to be a heptanol, and we're just going to number from right to left to give the OH the lowest number. Let's indicate the methyl groups and the ethyl groups. And when you get the hang of it, you find that you don't need to actually circle these methyl groups, but I find it helps just to get you started. Let's now write in where these alkyl groups are, and keeping in mind alphabetical order. So those are our alkyl groups, and 7 carbons means it's a heptan, so it's going to be a heptan 2-ol or a 2-heptanol. Now let's look at how we can draw based on the name. So we've got here 3-methyl-1-butanol. What we're going to do is start off with the longest chain of carbon atoms. Butanol indicates that there's 4 carbon atoms in the longest chain, and the 1 indicates that this OH group is on the first carbon. So I'm going to draw in my carbon chain here, and I'm just leaving a gap so that I can then fill up the remaining bonds with hydrogens. It's going to make it a lot more easier for us to draw the structure without having to draw all the bonds in. Let's go ahead and put this hydroxyl group in now. And you might realize that I've swapped the group around because I want to show that the oxygen is directly bonded to the carbon. Now I need to put in where this methyl group is. So it's on carbon number 3. So we've got 1, 2, 3. And the final step is just to fill up the rest of the bonds with hydrogens. So the first carbon with the OH group is going to contain 2. Next with 2. The next one with 1. And the last one with 3. So that would be a condensed formula for this alcohol. Second example, we've got 2,4-dimethylhexane-2-ol. So let's again draw the longest carbon chain. In this case, it's 6 carbon atoms with a hydroxyl group on carbon 2. Let's add in our methyl groups and finally fill in the rest of the bonds with carbon to hydrogen bonds. Our final example, we're just going to be looking at a diol, so there's going to be 2 hydroxyl groups. We've got 3-ethyl octan 1,4-diol, so let's start off with the longest carbon chain. Let's add in those hydroxyl groups and fill in the remaining bonds with hydrogens. I apologise if you can't quite see the part on the very right, but we've got a CH2 and a CH3 underneath there.